So picture this. You're standing on a job site, looking at a regular piece of everyday carbon steel, or maybe alloy steel, right there at room temperature, and you find yourself wondering, wait, is this thing ferrite or is it austenite? It's kind of the central mystery of the field for a lot of us, right? And honestly, getting it wrong, well, that can have some pretty serious real-world consequences for both safety and structural integrity. Welcome to today's Explainer. We're going to dive right into a super simple, practically foolproof framework to safely identify metal properties on the fly. We are talking about the rule of the exception. It's this incredibly high-efficiency method designed specifically for instant real-world application, so you can make fast, accurate evaluations without having to haul around a massive textbook. Okay, here's our roadmap for this explainer. First, we'll cover the basics of steel structures. Then, we'll look at the austenite three-piece set. After that, we'll compare the two structures. And we'll wrap the whole thing up with a really fun field mnemonic called Osam-Bulgogi. Let's jump in. Section 1. Basics of steel structures. Establishing the baseline rule. Listen, to actually use these metallurgical concepts out in the real world, we desperately need a straightforward baseline to sort of reduce the anxiety of over-memorizing. So here is the golden rule. I just want you to assume that all carbon and alloy steels in everyday room temperature applications are simply ferrite. That's it. Whether it's structural carbon steel or just your run-of-the-mill common alloy, just classify it as ferrite. You absolutely don't need to overthink the microscopic structures for everyday field use. When you start with this baseline assumption that literally everything is ferrite, you create this reliable default foundation that speeds up your entire decision-making process. It's a real game changer.
Moving right along, Section 2, Austenite three-piece set, the anomalies.
Okay, so since we've established that brilliant shortcut of assuming absolutely everything is ferrite, we really only need to memorize the exceptions. That makes life so much easier. We just need to know the specific anomalies that actually create an austenite structure at room temperature. We call this the austenite three-piece set, and it boils down to 3 exact chemical thresholds. Step 1, if a metal has 17% chromium and 8% nickel or more, boom, it's austenite. In fact, that famous 18-8 stainless steel you see literally everywhere, that falls perfectly into this very first step. Step 2, if it has 30% nickel or more, also austenite. And step 3, if it's packing 10% manganese or more, you guessed it, austenite. If the metal you're looking at doesn't hit at least one of these 3 specific chemical thresholds, well, you just revert right back to our baseline. It's ferrite. Actually, real quick before we move on, I want to drop a really fascinating little side note here about chromium. Anytime a metal hits at least 11% chromium, it officially crosses the threshold into being classified as stainless steel. No way, right? Just 11%? It's a great little numerical benchmark to just keep in your back pocket when you're out there evaluating materials on the job. All right, Section 3. Comparing the two structures. Form, function, and magnetism. So, knowing what these anomalies are is one thing, but understanding exactly why they behave so differently out in the real world is where this gets highly practical. Let's look at a side-by-side comparison. Starting with hardness, ferrite is, well, it's highly hard, while austenite is generally a bit lower. But here's the catch. Because ferrite is so hard, it can actually be quite vulnerable to breaking or fracturing under a heavy impact. Austenite, on the flip side, is super shock absorbent. And finally, the ultimate field test, magnetism. Ferrite is magnetic. A magnet is going to snap right onto it. Austenite, completely non-magnetic. It literally ignores magnets. So if you hold a magnet to a piece of steel and it doesn't stick, well, you're more than likely looking at one of our 3-piece set exceptions. Now, you might be wondering what's scientifically going on here. Why does austenite absorb shock so well, and why in the world does it completely ignore magnetic fields? Well, in the source material, there's this structural quirk beautifully described as having an empty center. Or if we look at the Korean term used, petsogi pia iki temune, which literally translates to because the stomach is empty. How cool is that? Because the microscopic crystalline center of the austenite structure is essentially hollow, it physically acts like a tiny little shock absorber when it gets struck. And that very same hollow center, it disrupts and breaks magnetic fields, which completely stops the magnet from sticking to it. It's absolutely crucial to remember this. It's a perfect example of structure dictating function. And that brings us to our final part. Section 4, Field Mnemonic, Osam-Bulgogi. Never forget the 3-piece set. Let's be real. Out on a busy, high-stakes job site, you don't have time to pull out reference charts. You need a quick, reliable way to remember these exact anomalies. So allow me to introduce a truly brilliant field mnemonic, Osam-Bulgogi. Now, for those of you who might not know, Osam-Bulgogi is this absolutely delicious, wildly popular Korean dish made of spicy squid and pork belly. Sounds great, right? But here, it literally becomes a lifesaver for our memory. Check this out. The O in Osam stands for Austenite, and Sam is actually the Korean word for the number 3, which represents our three-piece set. Put it together, and Osam equals the Austenite three-piece set. It's incredibly catchy and gives you instant, infallible recall of the exact anomalies you need to look out for. I mean, just picture this scenario for a second. Imagine you're out at a restaurant with your crew, grabbing dinner after a super long day on the job site. You're looking at the menu, you spot Osam-Bulgogi, and you decide to order it. Then, totally deadpan, you look right up at the waiter and playfully ask, "Excuse me, yeah, do you happen to have any ferrite to go with this Osam-Bulgogi?" The waiter's going to have absolutely no idea what you're talking about. But taking this highly technical metallurgical data and turning it into a hilarious, sticky mental movie like that, I guarantee you will never, ever forget the relationship between our baseline ferrite and the austenite three-piece exception. So as we wrap up this explainer today, I want to leave you with a quick thought. How will this simple rule change the way you look at everyday metals on your very next job site? By just assuming everything is ferrite right out of the gate, doing a quick test with a simple magnet, and remembering the Osam-Bulgogi three-piece set, you now have practical mastery over material identification. You've got this. Thank you so much for joining me for this structured breakdown. Stay curious, have fun out there, and above all, stay safe.